homework for 2.1 is due on Friday. If you need more time, you can ask for an extension and I'll add more time. If you need help setting up your homework account, just talk to me after class or write to me. Let's do Friday the 4th at 11:59 p.m. It has 5 questions, but it should take almost 3 hours to complete. Okay, so the notes were about the limit as x goes to a of your function f of x being equal to L. We talked about from approaching from the left side and from the right side, and there was a little bit of information missing from one of those descriptions. I think I'm going to go back through both of them, and we're going to get into the example I put up on the last class. Okay, so the limit as x goes to a of f of x equal to L, we wrote down this. So if you have notes, maybe look back in your notes and just fill in missing pieces, or if you want to rewrite this, I think it helps to learn by writing stuff down. The limit as x approaches a. That a is some real number. So we're approaching some real number a of the function f of x is L. And then someone also asked, will L be just one number, or is it possible to be different numbers? Remember that for a function, which we're looking at functions, every input has one output. So either you do have one number, or there is no actual value that you approach, or we'll get to it today that you're going to go to either positive infinity or negative infinity. So those are your choices. You get a number value, you get does not exist, or you get a positive or negative infinity. Then we did one-sided limits, and starting with the one from the left, this is where I want to put in some extra detail. So the limit as x approaches a from the left. From the left of f of x is equal to L. So the limit and then I'm going to put this part in where we're talking about of your function f of x. And this is happening as x goes to some number a on the left. This is the piece I left out. I forgot to talk about our function when we say all of this. And then I wrote down an explanation, and again, I left a little bit out of the explanation. So what we're looking at is x getting arbitrarily close to a. From the left. We have f of x getting arbitrarily close to L. Okay, and then we talked about the limit as x goes to a from the right, which we wrote down correctly, but I'll just write it one more time to be clear. And we're going to put in one little extra bit of detail where we have this limit as x approaches a from the right. Of f of x being equal to L. So the limit of your function f of x as x approaches a from the right. Is L. And then we wrote this down correctly. It's the same idea as over here. You're just going from the right side. So here, x gets arbitrarily close to a, and as that happens, f of x gets arbitrarily close to L. That's what we're looking for. I guess we'll just write it down one more time. And this a is some number a, some real number. I like to put it in little quotes, but you don't have to. Approaching this number from the right. And as that happens, we want to see if f of x gets arbitrarily to some other number. Okay, and then I brought up 3 cases. So case 1 was that your function approaches some number L and your function has an output equal to that limit right there. We did an example. The other one was where your function approaches some number L, but the function doesn't actually have an output right there. There's outputs close to that value, but no value of the function right at that number A. And then we got to case 3, where your function approaches some number L, but the output of the function is at some other spot. So there is an output, it's just not the same as the limit. It's larger or smaller or something somewhere else. Okay, we got to this example. For case number 3. So we're kind of looking at this particular number A and where the function sends A. It turns out the function sends that number A to some other value that's different from the limit. Our example is to have f of x equal to sine of x for x not equal to pi over 2. Also, as I'm kind of getting ready to draw this graph, I was thinking, I want to apologize for not having graded the welcome back quiz yet. I haven't had time. But those of you who have been concerned about it, I really just want to say that the math lab can be a very helpful place to go study. I have had some complaints here and there over the years about the tutors, so just check the tutoring schedule, find tutors that you like and times that you like to go study.
But where do you find tutors?
I'll share it as an announcement, but like I'll share it in Canvas where the lab is. But there's a math lab on campus in Brighton 118. They're open from 8 to 5, Monday through Friday, and it's free tutoring. I'll double check the room number, and sometimes they close early on Friday, so I'll let you know the schedule, and I'll post it in Canvas as an announcement. But there's free tutoring in there. There's a list of tutors, like there's a schedule so you can know who's there when, and when's a good time to go. And there's usually like 2 or 3 tutors working every hour. Also, I'll share information with you about PAL. So there's a PAL for Math 30. It's peer assisted learning. So you have people who are math mentors and they guide you through the class. I don't know if it's like a 1-unit thing or if it's just a group that you join, but I'll post that as an announcement as well. And there's another place where you can find help. Okay, so we're doing this function sine of x if x does not equal pi over 2. And we're going going to go to -3 when x equals pi over 2. Back to this just a minute. I worked in the math lab for a few years. I really like studying in a math lab. But, you know, sometimes there's not time in your schedule to visit. So you can also ask me for help. And just a reminder that we will do test corrections. So if things don't go well on your test, you can improve your score later on. So this graph is going to go through the origin.
Questions like for tests, we could redo it or something.
Yeah, I'll give instructions later, but if you get a score that's a low score, I'll let you redo problems and get at most a B.
Okay, awesome. Thank you.
For sure. Alrighty, we are going to start with just one cycle. The origin, pi, 2 pi. Height of 1 and down as low as negative. Yes. And at pi over 2, we move this one. Oh, we want to go down to -3. So taking care of this part, right at x equals pi over 2, the output is -3. All of the other outputs are on the graph of sine of x, and we're just going to have a hole right here. Can't get this labeled correctly. And it should go up to 1, but it has a missing spot right here. Down to -1.
To make it easier to look at, can you put like 3 pi over 2 between pi and 2 pi?
Yes.
Yeah, it can be quite confusing. It's been a while since some of us probably have took a math class in like a past semester, you know?
Yeah.
It can be quite confusing with the pi, like going from, yeah.
I'll keep that in mind too. When I make your test, maybe I'll possibly give you a graph instead of
Yes.
this problem.
Yes.
Okay, let's do this. Looks pretty good to me. So we're going through the origin up to a height of 1, right at pi over 2 over to 1. Maybe move this a bit. Back down through pi comma 0 and then to 3 pi over 2, and this should be at -1. It's a little better. And then back through, and then it keeps on oscillating like that. Okay, let's do the limit as x approaches pi over 2. from the left and the right. We're also going to label the function. Its name is f. Right there. The limit as x approaches pi over 2. Of your function f of x is equal to, somebody want to guess?
One.
Yes. Thank you. So the limit as x approaches pi over 2 of f of x is equal to 1. However, it just so happens that f of pi over 2 would be 3, or -3. So the limit is not exactly the same as where your function sends that number. It's what value the function approaches as you get closer and closer to that number.
Wait, quick question. Where'd you get the whole at 1 though?
It's from the information from the function, because the function said that the first part is to have sine of x for all values except for pi over 2, and at pi over 2, we're going to have an output of -3. So it's part of the instructions.
Okay, yeah, that makes sense. Thank you.
Yeah, always feel free to ask questions. I know it can be difficult, but it really helps everybody in the class. And again, this is coming from the instructions for your function, and it says that f sends this exact value to -3. It sends all of the other values that are getting closer and closer to pi over 2 up to 1. All right, that's the end of the example. And now we're going to talk about limits that approach positive or negative infinity. So some notation, it would look like the limit as x goes to a of f of x to be clear, it's going to be positive infinity or negative infinity. I'm going to write that down like this. So it's not both of them. It's going to be one or the other. So plus or minus infinity. So what this says is that as the function, or sorry, as x gets arbitrarily close to a, the function f of x will either grow without bound or decrease without bound to positive infinity or negative infinity. And a is some real number. So I'm gonna put little quotes here just so it doesn't look like the word a. Getting close to some number a, your function f of x grows without bound. Up to positive infinity. Or it decreases without bound down to negative infinity. So we're going to do an example. Bear with me while we draw this function. It's got three different pieces. And we're going to call it f. We're going to label x equal to 5. We will have a vertical asymptote at that value of x. Over here, on the negative side, for your x values, we're going to come down and over. So I don't know if you'll be able to see the blue color, but I'm going to highlight it with blue. Parts of the function are this color. Okay, and then on the other side, where it starts to have positive x values, we're going to come up and over, but not cross that asymptote. And then on the other side of x equal to 5, we're going to be going down, but not crossing the asymptote, and then up and over. This piece with this piece with this piece, all of that together is the function f. Let's look at the limit as x approaches 0 of f of x. And what is that equal to? Feel free to guess. This side, you're going to 0. Your function goes down to negative infinity. Same on the other side. As x gets closer and closer to 0 on the positive side, your function goes down to negative infinity. next one, we're going to have the limit as x approaches 5 from the left of f of x. This way, closer and closer to 5 with your x values. Your function is going up to positive infinity. X's are going this way. F of x's are going that way.
Wait, number 5 to the left, right? From the asymptote of 5 to the left, right?
Yeah, from the left.
So like start at 5 and then go left, right?
Yes.
Oh, then what happens if it's plus then? If it's 5 to the right then?
From the right, we're going down to negative infinity.
Okay. Try to figure that out. But why is that? I don't see the negative infinity. Why does it go negative? Can you like?
Because this time your x values are going towards 5 on the right side, this way. And you follow your
wait.
f of x values down that way.
Oh wait. So plus and negative means like it's going towards 5, not like.
Yeah.
Oh, okay, yeah. I think I got confused by that. Okay, I think I understand now. Thank you.
Let's see if there's another one I want to look at. The last part here is, since the limit on the left side is not the same as the limit on the right side, what we would say is that as x approaches 5 on the left and the right of f of x does not exist. Okay, we're going to do another example. I want to give my function a new name, but maybe that'll make it kind of messy. Okay, this, we're going to use the same name, but it's a whole new function, whole new example. So starting over with some function f being, we're just going to draw a graph. Kind of it was the same idea. I put a vertical asymptote at 5. There's nothing super special about 5. It's just a number I picked. And I had my function right here on the negative side for x values. And then on the positive side, we're going to come up and over, but not cross that asymptote. And then over here, we're going to have the function continue like this. And we're going to use the same name, f. I'm going to start with x approaching 0 from the left.
I think it would be a good refresher if you like try to like make a try to like figure out what kind of equation is the like the curve it would be nice refresher if like if you could write like a what kind of write the equation for the curves like the u curves not like the other slope the u curves
Okay.
at the
I might have an example like that next, but for now we're going to just go with only knowing what the graph is and not what the function is doing.
okay yeah
I know what you mean.
yes yeah
We'll do that too.
yes
Okay, but your homework will probably have one where you don't know exactly what your function's doing and all you have is the graph. So we want to practice this first.
okay yeah
Okay, practice.
got it.
Let's do going to 0 on the left side. Your function's going to positive infinity. And next, go to 0 on the right. The limit as x approaches 0. Of whatever this function is, f. So looking at the graph, you're going closer and closer to 0 on this side. Now your function is going down to negative infinity. Okay, so since we're approaching 0 on the left and the right, but the limits don't match, what we would say is that as x, the limit as x approaches 0 of f of x does not exist.
Wait, can you give us some more time to write this down? I'm trying to figure it out too.
Oh yeah, and we're going to look at one more limit before we leave this picture, this graph. Put it down here. So down here, we'll do the limit as x approaches 5. So first, let's look at the left side. Okay. X is going to 5 from the left. F of x goes up to positive infinity. Then as x goes to 5 on the right, same thing's happening. So as x approaches 5, f of x goes to positive infinity. Okay, I'm going to think of another example. So leave this here for a moment. Let me run around. So there's a good example coming up, but I introduced.
I would like to ask something real quick.
Yeah.
Those are exponential functions, by the way, right? You know the two lines between the tangent one. I think.
Yeah. I'm not super sure about saying that they're exponential, but these are functions that have vertical asymptotes, is kind of what I
Okay.
am trying to.
Yeah.
That's what we're gonna.
Yeah. Okay. Yeah. It's okay. It's okay.
Okay. Because the exponential function is the one that goes, it's like, it approaches,
Yeah.
it's a certain name that I'm kind of like, that's like a particular name that maybe we can't use, but let's talk about vertical asymptotes. So it might be called exponential, but I'm not super comfortable saying that, so I don't know. Reading the list. So I wrote computing limits that go to positive or negative infinity without having a graph. So I recommend that you look for and use vertical asymptotes. And I'll put a reminder on how to find those. The function f of x being a fraction with a function p of x in the numerator, q of x in the denominator, has a vertical asymptote when q of x is equal to 0. Also a note that you don't want that to also occur if p of x is equal to 0. It's much louder than I had planned. Okay, we'll put that note down and then call it good for today. So you need p of x not equal to 0. I'll show you the example we'll do, but we're going to wait till next class to actually work through it. It's having f of x being equal to 1 over x. And I'm going to go ahead and put, like, when we come back to class, I'll put down a table of inputs x, outputs f of x to get an idea of what's happening. And then we'll look at limits and we'll keep on working with notes for 2 point. We're still in 2.2. Okay, I'll see you on Friday. Thank you, everyone.